Hello everyone, and welcome to my channel. Here, we explore the fascinating world of science, from the mysteries of the universe to the wonders of everyday life. Sit back, relax, and let's discover something amazing together. Have you ever looked up at the night sky and wondered how big the universe really is? Or where we are within it? Today, I would like to take you on a journey beyond our planet, beyond our solar system, and into the vast universe that surrounds us. We will explore the structure of the cosmos, the birth and death of stars, black holes, the expansion of space, and even the possibility of life beyond Earth. The universe is about 13.8 billion years old. It contains billions of galaxies, and each galaxy contains billions of stars. Our planet, Earth, is just a small world orbiting an ordinary star in the Milky Way galaxy. Yet from this small planet, we have learned incredible things about space and time. Through science and observation, humanity has discovered that we are not the center of the universe, but we are part of something much greater. So today, let us explore not only the size and structure of the universe, but also what it means for us as human beings. Have you ever looked up at the night sky and quietly wondered where we are in this immense universe? Perhaps it happened on a peaceful evening, when the air was still and the stars appeared one by one like distant lanterns. Perhaps you were away from the bright lights of the city, where the sky seems deeper, darker, and infinitely layered. In those moments, something shifts inside you. The world feels both larger and smaller at the same time. Larger, because you begin to sense a vastness beyond imagination. Smaller, because you realize how tiny our planet truly is within that endless expanse. Tonight, we begin a gentle journey through the universe, not in a rush, not with overwhelming equations or complicated formulas, but with curiosity and reflection. We will explore soft yet astonishing truths about space, its size, its history, its mysteries, and its quiet beauty. This is not only a scientific exploration, it is also an emotional one. The universe is often presented as a collection of numbers, billions of galaxies, trillions of stars. Distances measured in light years so large that they almost lose meaning. But behind those numbers lies something far more powerful: perspective. When we learn about the universe, we are not just learning about distant objects floating in darkness. We are learning about our place within a much larger story. Science gives us structure and explanation. It tells us how stars are born, how galaxies move, and how time itself behaves under extreme conditions. Yet beyond the data, there is something deeply human in the act of looking up at the sky. For thousands of years, long before telescopes or satellites existed, people stared at the same stars and asked similar questions. Ancient civilizations mapped constellations. Philosophers debated the nature of existence. Sailors navigated using distant points of light. The sky has always been both a guide and a mystery. Today, with advanced technology, we can see farther than ever before. Powerful telescopes orbit our planet and send back breathtaking images of nebulae glowing in brilliant colors, of galaxies colliding in slow cosmic dances, of planets forming around newborn stars. We can measure the faint radiation left behind from the very beginning of the universe. We can detect planets orbiting distant suns. In many ways, we are living in a golden age of cosmic discovery. And yet, despite all this knowledge, the universe remains beautifully humbling. Consider this: every human being who has ever lived, every story, every triumph, every sorrow, has unfolded on a small rocky planet orbiting an ordinary star in a galaxy among billions. All of history, all of art, all of music, all of love, has taken place within a tiny fraction of the observable cosmos. When you pause and reflect on that, it can feel overwhelming, but it can also feel strangely comforting. The universe does not diminish our importance. Instead, it reshapes it. Our significance is not found in size or dominance. It is found in awareness. We are small, yes, but we are capable of understanding. We are made of atoms forged inside ancient stars. The carbon in your body, the oxygen you breathe, the iron in your blood, all were created in stellar furnaces billions of years ago. In a very real sense, you are a part of the cosmos becoming conscious of itself. This journey through the universe is not about proving how insignificant we are. It is about appreciating the delicate balance between smallness and meaning. When we learn how far galaxies are from one another, we do not disappear into nothingness. Instead, we gain a deeper appreciation for the fragile and precious nature of our own world. Imagine standing under a clear sky and realizing that the light reaching your eyes began its journey years, decades, or even thousands of years ago. Some stars you see tonight may no longer exist in the same form. You are witnessing history written in light. Every glance upward is a glimpse into the past. That idea alone changes how we think about time, space, and even ourselves. Throughout this exploration, we will move gently from the largest scales, the observable universe itself, down to our home galaxy, our solar system, and even the life that may exist beyond Earth. We will consider black holes, dark energy, and the expanding fabric of space. We will reflect on philosophical questions about meaning and existence. And along the way, we will try not just to understand, but to feel. Because the universe is not only vast, it is also quiet. It expands slowly. Stars evolve over millions and billions of years. Galaxies drift apart in almost imperceptible motion. Compared to the speed of human life, the cosmos moves with patient calm. There is something peaceful in that rhythm. It reminds us that not everything must happen at once. Not every mystery must be solved immediately. As we begin, allow yourself to hold both curiosity and calmness. Let the numbers amaze you, but let the silence comfort you. The universe does not rush. It simply exists, ancient, expansive, and filled with subtle wonder. In the chapters ahead, we will explore how large the universe truly is, where our galaxy fits within it, how stars live and die, how time bends, and whether we might be alone. Each step will reveal not only scientific truth, but also perspective. Because perhaps the most beautiful part of studying the universe is not that we will someday understand it completely. Perhaps the most beautiful part is that we can look up at the night sky at all, and feel that quiet sense of awe. How large is the universe? It sounds like a simple question. Yet the answer stretches the imagination so far that language itself begins to feel small. When scientists speak of the observable universe, they are referring to the portion of the cosmos we can, in principle, see from Earth. Not because it is the entire universe, but because light has had enough time to reach us since the beginning of cosmic expansion. The universe is about 13.8 billion years old. So at first glance, you might assume that the farthest distance we could see would be 13.8 billion light-years. But the reality is even more astonishing. Because the universe has been expanding during all that time. The most distant light we detect today comes from regions that are now about 93 billion light-years across in diameter. 93 billion. The number feels abstract, almost poetic in its impossibility. A light-year, by the way, is the distance light travels in 1 year, about 9.46 trillion kilometers. Light moves at roughly 300,000 kilometers per second. It could circle Earth more than 7 times in a single second. And yet, even at that incredible speed, it takes years to travel between stars, and billions of years to cross intergalactic space. When you hear that the observable universe spans about 93 billion light-years, you are hearing about distances so vast that even light, the fastest thing we know, struggles to bridge them within the lifetime of the cosmos itself. And within that enormous volume are galaxies. Not just dozens, not just thousands, but an estimated 2 trillion galaxies. According to studies using data from the Hubble Space Telescope, each galaxy contains millions, billions, or even trillions of stars. Pause for a moment and consider this. Every star you see with your naked eye belongs to just one galaxy, our own. And yet there are trillions more galaxies beyond it. If Earth were the size of a grain of sand, the observable universe would still stretch beyond imagination. The comparison almost feels unfair, like comparing a single heartbeat to the age of mountains. The distances between galaxies are equally breathtaking. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. The light reaching your eyes from Andromeda tonight began its journey when early humans were just beginning to craft stone tools. That light has traveled patiently through intergalactic darkness, uninterrupted, until it touches your retina. Most galaxies are much farther apart. Vast stretches of near-empty space lie between them, regions so sparsely populated that even a single atom per cubic meter can be considered relatively dense. Space is not entirely empty, but it is astonishingly thin. The universe is less like a crowded city and more like an endless desert, where galaxies are rare, luminous oases separated by unimaginable distances. And yet, this vastness carries a quiet lesson. The speed of light defines what we can observe. No signal can travel faster. This means there is a cosmic horizon beyond which we cannot see, not because nothing exists there, but because its light has not had time to reach us. Beyond that horizon, the universe may continue infinitely, or it may curve back on itself in ways we do not yet fully understand. Current measurements suggest the universe is remarkably flat on large scales, but whether it is truly infinite remains an open question. There is something humbling about this limit. No matter how powerful our telescopes become, there will always be regions forever beyond our view. The universe gently reminds us that knowledge has boundaries, at least for now. And then there is Earth. Our planet orbits a medium-sized star in the outer region of a spiral galaxy. We are not near the galactic center. We are not in a particularly dramatic location. There is no cosmic spotlight shining on our coordinates. We are simply here, on a small, rocky world covered in oceans and clouds. From space, Earth appears as a pale blue dot. That phrase became famous after astronomer Carl Sagan used it to describe a photograph taken by the Voyager 1 spacecraft in 1990. From nearly 6 billion kilometers away, Earth was barely visible, just a tiny speck suspended in a beam of sunlight. Every human conflict, every celebration, every invention, every quiet evening at home has taken place on that dot. When you reflect on the scale of the universe, it can initially feel disorienting. If we are so small, does anything matter? But perhaps size is not the measure of meaning. A single cell in your body is microscopic, yet it plays an essential role in keeping you alive. Smallness does not equal insignificance. Earth may be tiny in cosmic terms, but it is enormous in experience. It holds oceans, forests, languages, dreams. The vastness of the universe does not erase us. Instead, it provides contrast. Against an immense backdrop, the details of our world become sharper, more precious. There is also something strangely comforting about cosmic scale. The problems that feel overwhelming in daily life shrink slightly when placed beside galaxies. The universe has endured for billions of years. Stars have exploded and reformed. Entire galaxies have collided and reshaped themselves. And through it all, existence continues. We are part of that ongoing story. Even our bodies are composed of elements formed in ancient stars. Hydrogen emerged shortly after the Big Bang. Heavier elements, carbon, oxygen, iron, were forged in stellar cores and scattered into space by supernova explosions. Over time, gravity gathered that enriched material into new stars and planets. Eventually, on at least one small world, chemistry became biology. You are not separate from the universe. You are made of it. When you next look at the night sky, imagine the immense three-dimensional structure behind those points of light. Imagine billions of galaxies stretching in every direction. Imagine light traveling for millions of years just to reach you. And then imagine yourself, a conscious being capable of understanding this scale, however imperfectly. The universe is vast beyond easy comprehension. It stretches across distances that dwarf our language and our lifetimes. Yet within that immensity, you are here, aware, asking questions. And that awareness may be one of the rarest phenomena of all. In the next chapter, we will move from the unimaginable scale of the universe down to something closer, our galactic home, the Milky Way. We will explore its structure, its stars, and our quiet position within its swirling arms. Because even in a universe of trillions of galaxies, home still matters. After contemplating the vastness of the observable universe, It feels almost comforting to come closer, to return to something more intimate. Among the trillions of galaxies scattered across cosmic space, there is one that holds every star you have ever seen with your own eyes. One that contains our sun, our planets, and the quiet blue world you call home. This galaxy is the Milky Way. On a clear night far from city lights, you can actually see it. A faint, misty band stretches across the sky. Like spilled milk poured gently from horizon to horizon. Ancient cultures told stories about it. The Greeks imagined it as milk from the goddess Hera. In many Asian traditions, it was seen as a river separating two lovers in the sky. Long before modern astronomy, humans sensed that this glowing band was something special. Today, we know it is not a cloud, not a river, but a vast spiral galaxy seen from within. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped region of stars with spiral arms extending outward. If you could step far outside it and look back, you would see a luminous whirlpool of light, arms curved gracefully around a bright core. Its diameter is about 100,000 light-years across. That means even traveling at the speed of light, it would take 100,000 years to cross from one side to the other. Let that settle for a moment. Light, moving faster than anything else in existence, would need 100 millennia to span our galaxy. Within this vast structure are an estimated 100 to 400 billion stars. The exact number is uncertain because counting stars in a galaxy from inside it is not easy. It is like trying to count every tree in a forest while standing among the trunks. And our sun? It is only one of those hundreds of billions. We are located in a small spiral arm called the Orion Arm, about 26,000 light-years from the galactic center. This position is neither too close nor too far. Near the center of the Milky Way lies a supermassive black hole known as Sagittarius A star. It has a mass about 4 million times that of our Sun. Stars orbit it at incredible speeds, guided by its immense gravitational pull. Fortunately, we are at a safe distance. If we were much closer to the center, radiation and gravitational disturbances might make stable planetary systems difficult. If we were too far out, there might not be enough heavy elements to form rocky planets like Earth. In a quiet way, our position is fortunate, balanced, stable, unremarkable in the best possible sense. The Sun takes about 225 to 250 million years to complete one full orbit around the center of the Milky Way. This is sometimes called a cosmic year. Since its formation about 4.6 billion years ago, the Sun has orbited the galaxy roughly 20 times. That means the last time the Sun was in its current position in the galaxy, dinosaurs had not yet appeared. Continents were arranged differently. Life on Earth was entirely unfamiliar. The galaxy moves, even if we do not feel it. And within it, there is structure beyond just stars. Vast clouds of gas and dust drift between them. These regions, known as nebulae, are stellar nurseries where new stars are born. Under the force of gravity, gas collapses inward, heating up and eventually igniting nuclear fusion. A star begins to shine. Some of the most beautiful images ever captured by telescopes come from these nebulae. Pillars of gas sculpted by radiation, glowing clouds illuminated in reds and blues. They are not silent places. They are dynamic, energetic, constantly reshaping themselves over millions of years. Yet on human timescales, the galaxy feels steady, calm. If you step outside at night and see the Milky Way arching overhead, you are looking along the dense plane of the galaxy. The misty glow comes from countless distant stars too faint to distinguish individually. What appears soft and continuous is actually a layered depth of light, star upon star upon star. There is something quietly humbling about realizing that every visible star belongs to this single structure. We do not see other galaxies with the naked eye easily, except perhaps Andromeda under very dark skies. The rest of the cosmos remains hidden without telescopes. The Milky Way is our luminous neighborhood. And yet, even within this neighborhood, distances are enormous. The nearest star system to us, Alpha Centauri, is about 4.3 light-years away. That means its light takes over 4 years to reach Earth. If our fastest spacecraft today attempted to travel there, it would take tens of thousands of years. Interstellar space is not empty in the dramatic sense, but it is incredibly sparse. The average distance between stars in our region of the galaxy is about 5 light-years. 5 light-years of mostly nothing. The galaxy, then, is not a crowded marketplace of stars brushing against one another. It is more like a vast countryside at night, with distant lights glowing gently across a dark plain. And still, within this immense structure, there is order. Stars orbit the galactic center. Spiral arms rotate slowly. Gravitational interactions shape clusters and stellar streams. Over billions of years, galaxies even merge. In fact, the Milky Way and the Andromeda Galaxy are moving toward each other and are expected to collide in about 4 billion years. Collide sounds violent, but because of the enormous distances between stars, actual stellar collisions are unlikely. Instead, the galaxies will pass through one another in a slow gravitational dance, reshaping into a new, larger galaxy over time. Cosmic events unfold with patience. When you think about the Milky Way, imagine its full scale, 100,000 light-years wide, containing hundreds of billions of stars, rotating gracefully around a hidden center. Imagine our Sun quietly orbiting within one modest spiral arm. Imagine Earth, a small planet circling that star, carrying oceans and life. We are not at the center of the galaxy. We are not at its edge. We are simply somewhere within it, and that is enough. There is beauty in not being central. Because from this unassuming position, you can look outward. You can study nebulae, measure stellar motion, detect exoplanets, and even observe the faint glow of the universe beyond our galaxy. The Milky Way is our home, but it is also our window. In the next chapter, we will move even closer, from the scale of the galaxy down to the star that anchors our daily lives, the Sun, and the family of planets that orbit around it. From billions of stars, we return to one. After drifting through the vast spiral arms of the Milky Way, it feels grounding to return to something familiar, to the steady glow that rises each morning and warms your skin. Among the hundreds of billions of stars in our galaxy, there is one that matters more to you than any other: the Sun. At first glance, the Sun may seem extraordinary. It dominates our sky. It fuels life. It defines day and night. But in cosmic terms, the Sun is considered an average star, a G-type main sequence star, sometimes called a yellow dwarf. It is neither the largest nor the smallest, neither the hottest nor the coolest. It shines steadily, converting hydrogen into helium through nuclear fusion in its core. Every second, the Sun fuses about 600 million tons of hydrogen into helium. In the process, a small portion of mass is converted into energy, following Einstein's famous equation, E equals mc squared. That energy travels outward through the Sun's layers, eventually radiating into space as light and heat. It takes about 8 minutes for sunlight to travel from the Sun to Earth. When you feel warmth on your face, you are experiencing energy that left the Sun 8 minutes earlier, and before that, it may have taken hundreds of thousands of years to travel from the Sun's core to its surface. Light moves quickly through space, but inside a star, it bounces slowly, gradually making its way outward. The Sun is about 4.6 billion years old and is expected to shine for roughly another 5 billion years. It is stable now, in the long middle phase of its life. But stars evolve. Eventually, the Sun will exhaust its hydrogen fuel, expand into a red giant, and later shed its outer layers, leaving behind a dense core called a white dwarf. This transformation lies far in the future, far beyond any human timeline. For now, the Sun remains steady, a quiet engine at the center of our solar system, and around it orbit the planets. 8 major planets move in elliptical paths, held by gravity. Closest to the Sun is Mercury, a small, rocky world with extreme temperatures. Because it lacks a thick atmosphere, its surface swings between scorching heat and freezing cold. A single day on Mercury, one full rotation, lasts about 59 Earth days. Next comes Venus, often called Earth's twin because of its similar size. But Venus hides a dramatic difference. Its thick atmosphere traps heat through a runaway greenhouse effect, making it the hottest planet in the solar system. Surface temperatures can melt lead, Beneath its clouds lies a world both familiar in shape and hostile in environment. Then there is Earth. The third planet from the Sun occupies a special position, often referred to as the habitable zone. Here, temperatures allow liquid water to exist on the surface. Earth's atmosphere protects life from harmful radiation while maintaining a delicate balance of gases. Oceans cover about 70% of its surface. So far, it remains the only known planet to support life. Beyond Earth lies Mars, the red planet. Its rusty color comes from iron oxide on its surface. Mars once had liquid water flowing across its terrain, and scientists continue to study it for signs of past microbial life. Though cold and dry today, it remains a focus of exploration and possibility. After Mars, we enter the realm of the gas giants. Jupiter is the largest planet in the solar system, so large that more than 1,000 Earths could fit inside it. Its powerful gravity influences the orbits of other bodies and may have played a protective role in deflecting comets from the inner planets. Jupiter's Great Red Spot, a massive storm, has been raging for centuries. Saturn follows, adorned with its iconic rings. These rings are composed of ice and rock particles, ranging from tiny grains to large fragments. Though they appear solid from a distance, they are delicate structures, orbiting in graceful formation. Farther still are Uranus and Neptune, the ice giants. Uranus rotates on its side, giving it extreme seasonal variations. Neptune, deep blue and distant, experiences powerful winds that sweep across its atmosphere at astonishing speeds. Between and beyond these planets lie countless smaller bodies, dwarf planets like Pluto, asteroid belts, comets, and icy objects in the Kuiper Belt and the distant Oort cloud. The solar system is not just 8 planets, it is a complex family of worlds, each shaped by gravity and time. The distances between planets are vast. Even at the speed of modern spacecraft, travel takes months or years. Light itself needs hours to reach the outer planets. The solar system, though small compared to the galaxy, is still enormous by human standards. And yet, there is order in its motion. Planets orbit in nearly the same plane, remnants of the rotating disk of gas and dust from which they formed. About 4.6 billion years ago, this cloud collapsed under gravity. Most of its material gathered into the Sun, while the rest flattened into a spinning disk. Over time, particles collided and stuck together, forming planetesimals, then protoplanets, and eventually the planets we know today. The solar system is the result of gradual accumulation, countless small collisions building something stable. When you look at the Sun during sunrise or sunset, when it glows softly at the horizon, it may seem eternal. But it is part of a story that began with a collapsing cloud of gas in a spiral arm of the Milky Way. It is one star among many, and yet it is the reason oceans shimmer, plants grow, and life thrives here. There is something quietly beautiful about this arrangement. A single star, steady and average, surrounded by diverse worlds moving in patient orbits. Gravity holds them together like an invisible thread. And you, standing on one of those worlds, are carried through space at incredible speeds, orbiting the Sun, orbiting the galaxy, without ever feeling the motion. In the next chapter, we will move beyond our solar system and explore the lives of stars themselves, how they are born, how they shine, and how they eventually transform into some of the most fascinating objects in the universe. Because the Sun is only one chapter in a much larger stellar story. After exploring our Sun and its planetary family, you may begin to wonder about the countless other stars scattered across the galaxy. They appear steady from Earth, tiny, flickering points of light that seem eternal. Yet stars are not fixed or unchanging. They are born, they evolve, and eventually, they die. And in their life cycles, they create the very ingredients that make planets and life possible. A star begins its story inside a vast cloud of gas and dust known as a molecular cloud. These clouds drift quietly in the galaxy, cold and dark, composed mostly of hydrogen. Over time, gravity gently pulls regions of the cloud inward. As the material collapses, it grows denser and hotter. You can imagine it like a slow gathering of breath, the cloud tightening, concentrating, warming. When the temperature at the core becomes high enough, about 10 million degrees Celsius, nuclear fusion ignites. Hydrogen atoms begin fusing into helium. At that moment, a star is born. Radiation from fusion pushes outward, balancing the inward pull of gravity. This balance creates stability. A star enters what astronomers call the main sequence phase of its life. Our Sun is currently in this stage. During this long period, which can last billions of years, the star steadily fuses hydrogen in its core. For stars similar to the Sun, this phase is calm and relatively predictable. But not all stars are the same. Stars come in different masses, and mass determines destiny. Small stars, known as red dwarfs, burn their fuel slowly and carefully. They can shine for trillions of years, far longer than the current age of the universe. Massive stars, on the other hand, live fast and intensely. They burn hotter and brighter, using up their hydrogen much more quickly. A star 10 times the mass of the Sun may live only tens of millions of years. Brightness, in the universe, often means brevity. As hydrogen in the core begins to run out, the balance between gravity and pressure shifts. The core contracts, heating up further. In stars like the Sun, this causes the outer layers to expand dramatically. The star becomes a red giant. Its surface cools and reddens, but its overall size increases enormously. In several billion years, our Sun will enter this phase. It will expand so much that it may engulf Mercury and Venus. Earth's fate is uncertain, but conditions here would become uninhabitable long before that expansion reaches us. Yet even in this transformation, there is beauty. Inside red giants, new fusion reactions occur. Helium atoms fuse into carbon and oxygen. In more massive stars, fusion continues even further, creating heavier elements such as neon, silicon, and eventually iron. Iron is special. Fusing iron does not release energy, it consumes it. When a massive star builds up an iron core, fusion can no longer support the outward pressure needed to resist gravity. The core collapses suddenly and catastrophically. What follows is one of the most powerful events in the universe, a supernova. In a fraction of a second, the core compresses and rebounds. A shockwave tears through the outer layers, blasting material into space. For a brief time, a single exploding star can outshine an entire galaxy. Heavy elements, gold, uranium, and many others, are forged in these extreme conditions and scattered into interstellar space. The calcium in your bones, the iron in your blood, the gold in jewelry. Much of it was formed in ancient stellar explosions. Stars do not simply end. They transform and give back. What remains after a supernova depends again on mass. Some stars leave behind neutron stars, incredibly dense objects where protons and electrons have merged into neutrons. A teaspoon of neutron star material would weigh billions of tons on Earth. Others collapse even further into black holes, regions where gravity becomes so strong that not even light can escape. These mysterious objects will be explored more deeply in the next chapter. For smaller stars like the Sun, the ending is gentler. After shedding their outer layers into space, forming glowing shells called planetary nebulae, they leave behind white dwarfs. A white dwarf is the hot, dense core of the former star, slowly cooling over billions of years. No dramatic explosion, no violent collapse, just a quiet fading. Across the galaxy, stars are constantly forming, evolving, and ending. Some are just beginning their luminous lives in nebulae. Others are nearing their final transformations. The Milky Way is a tapestry woven from these countless stellar stories. When you look up at the night sky, you are seeing stars in many different stages of life. Some may no longer exist in the form you see. Their light is simply still traveling toward you. Others are newly formed, shining brightly for the first time. Time in the universe is layered. A star that appears steady to you may already be gone. A supernova that exploded thousands of years ago may just now be visible from Earth. The sky is not a snapshot of the present. It is a collage of different moments. And within this grand cycle, there is continuity. The gas and dust expelled by dying stars enrich interstellar clouds. New stars form from that enriched material. Planets emerge from the leftover disks. On at least one such planet, life began. Eventually, conscious beings evolved and began to study the stars that created them. You are part of this cycle. The atoms that compose your body once drifted in space, born in ancient stellar furnaces. Over billions of years, they were gathered by gravity into Earth, into living organisms, into you. The life cycle of stars is not separate from your own existence. It is your origin story written across cosmic time. In the next chapter, we will focus on one of the most mysterious results of stellar evolution: black holes. Though often imagined as destructive and frightening, they are also fundamental parts of galactic structure and cosmic balance. From gentle births in nebulae to dramatic endings in supernovae, stars shape the universe. And in doing so, they have shaped you. Among all the objects in the universe, few capture the imagination quite like black holes. The name alone feels dramatic, dark, final, absolute. For many years, black holes were treated almost like cosmic monsters, swallowing everything in their path, erasing light and matter without mercy. In science fiction, they are often portrayed as dangerous gateways or catastrophic threats. But the real story is quieter, more subtle, and in many ways, more beautiful. A black hole forms when a massive star reaches the end of its life. As you learned in the previous chapter, when such a star can no longer sustain fusion in its core, gravity takes over. The core collapses inward under its own immense weight. If the remaining mass is great enough, nothing can stop that collapse. The matter compresses into an incredibly small region, creating a gravitational field so strong that not even light can escape. That boundary, the point beyond which escape becomes impossible, is called the event horizon. It is not a solid surface. There is no dramatic wall or edge in the ordinary sense. The event horizon simply marks the distance from the center where the escape velocity exceeds the speed of light. Cross that boundary, and every possible path leads inward. From the outside, however, black holes are not cosmic vacuum cleaners roaming space. They do not wander randomly, consuming stars like hungry creatures. They obey the same laws of gravity as any other object. If our sun was suddenly replaced by a black hole of equal mass, which is not physically possible, but imagine it for a moment, Earth would continue orbiting in exactly the same way. The gravitational pull at our distance would remain unchanged. Black holes are powerful, but they are not magical. There are different sizes of black holes. Stellar mass black holes form from collapsing stars and may have masses several times that of our Sun. Supermassive black holes, however, are far larger. These giants sit at the centers of most galaxies, including our own Milky Way. At the center of the Milky Way lies Sagittarius A*, a supermassive black hole with a mass about 4 million times that of the Sun. It does not devour the galaxy. Instead, it plays a stabilizing role. Stars orbit around it in long, elliptical paths. Its gravity helps anchor the galactic core. In recent years, astronomers have even captured images of black holes. In 2019, the Event Horizon Telescope released the first image of a black hole's shadow, a glowing ring of light surrounding a dark center. The image was not a photograph in the everyday sense, but a composite created from data gathered by radio telescopes around the world. Still, it marked a profound achievement, direct visual evidence of something once considered purely theoretical. Einstein's theory of general relativity, published in 1915, predicted the possibility of black holes. For decades, they were mathematical solutions, strange but abstract. Now we observe stars orbiting invisible masses. We detect gravitational waves from black hole mergers. We see their influence in the behavior of surrounding matter. And yet, despite their extreme nature, black holes are not endless voids of destruction. They influence their surroundings primarily through gravity. If matter drifts too close, it may form an accretion disk, a swirling disk of gas and dust spiraling inward. As this material accelerates and heats up, it can emit intense radiation, sometimes outshining entire galaxies. These active galactic nuclei are among the brightest objects in the universe. But even then, most of space remains vast and sparse. The average distance between stars is so large that collisions or close encounters with black holes are rare on cosmic timescales. There is also a subtle beauty in the physics of black holes. Near the event horizon, time itself behaves differently. According to general relativity, strong gravity slows the passage of time. To a distant observer, an object falling toward a black hole appears to slow down as it approaches the event horizon, fading gradually. From the perspective of the falling object, however, time continues normally, at least until tidal forces become extreme. This bending of time and space reminds you that the universe is not rigid. Space can curve. Time can stretch. Gravity shapes reality itself. And black holes are not entirely eternal. Stephen Hawking proposed that black holes can slowly emit radiation, now called Hawking radiation, due to quantum effects near the event horizon, over incredibly long timescales. Far longer than the current age of the universe, black holes may gradually lose mass and eventually evaporate. The process is extraordinarily slow, especially for supermassive black holes, but it suggests that even these dark giants are not permanent. Nothing in the universe remains unchanged forever. When you hear the phrase black hole, you might imagine darkness swallowing everything. But perhaps a better image is that of an anchor, a deep gravitational well shaping its environment quietly and predictably. They are not enemies of light. They are part of the structure of galaxies. In fact, without supermassive black holes, galaxies might not form in the same way. Their gravitational influence affects star formation and galactic evolution. They are woven into the fabric of cosmic development. There is something calming in this realization. Even the most extreme objects in the universe follow laws. They are not chaotic in a reckless sense. They are expressions of gravity carried to its limits. When you look at the night sky, you cannot see black holes directly. They are invisible against the darkness. And yet, they are there, shaping orbits, influencing motion, participating in the slow choreography of galaxies. The universe contains mystery, yes, but mystery does not equal menace. In the next chapter, we will explore something even more subtle, time itself. How it stretches, how it bends, and how looking into space is actually looking into the past. Because in the universe, distance and time are inseparable. Time feels steady to us. Seconds pass with the same rhythm. Days follow nights in quiet certainty. Our clocks tick with confidence. And we trust them without question. Yet in the vastness of the universe, time is far less rigid than it appears. It stretches, bends, slows, and even warps under the influence of gravity and motion. The deeper we look into space, the more we discover that time is not simply something we move through, it is something woven into the very fabric of reality. To understand time in the universe, we begin with Albert Einstein's theory of relativity. In the early 20th century, Einstein proposed something extraordinary. Space and time are not separate. They form a single entity known as space-time. Massive objects like stars and planets do not merely sit within space, they curve space-time around them. And this curvature affects how time flows. This leads to one of the most astonishing discoveries in physics: time dilation. Time dilation means that time does not pass at the same rate everywhere. If you travel at speeds close to the speed of light, time for you will move more slowly compared to someone who remains at rest. Similarly, if you are near a very strong gravitational field, such as near a massive star or a black hole, time will also slow down relative to someone far away. This is not science fiction. It has been measured and confirmed. Astronauts aboard the International Space Station age ever so slightly more slowly than people on Earth because they are moving faster relative to the planet's surface. Even GPS satellites must account for time dilation. Their onboard clocks tick at a slightly different rate due to both their speed and their position in Earth's gravitational field. Without correcting for relativity, GPS systems would quickly become inaccurate. Time, then, is not absolute. It is flexible. Near a black hole, the effects become dramatic. As you approach a black hole's event horizon, time from the perspective of a distant observer appears to slow down almost to a stop. Light escaping from near the event horizon becomes increasingly redshifted and delayed. To an outside observer, an object falling into a black hole seems to freeze at the edge, fading slowly away. Yet for the falling object itself, time feels normal, until it reaches the extreme conditions inside. The universe, therefore, is not governed by a single universal clock. Every observer carries their own timeline, shaped by motion and gravity. Another remarkable concept is light time. Light travels at approximately 300,000 kilometers per second, the fastest speed possible in the universe. But even at that extraordinary speed, light takes time to cross space. When you look at the moon, you see it as it was about 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. If the sun were to suddenly disappear, which it won't, we would not know for 8 minutes. As distances increase, this effect becomes profound. The nearest star beyond our Sun, Proxima Centauri, is about 4.24 light-years away. This means the light we see from it tonight left that star over 4 years ago. When we observe distant galaxies billions of light-years away, we are looking billions of years into the past. Astronomy, in this sense, is time travel through observation. Telescopes are not just instruments that magnify space, they are machines that reveal history. When astronomers observe galaxies 10 billion light-years away, they are seeing those galaxies as they were 10 billion years ago. Some of the most distant galaxies observed today show the universe in its infancy, only a few 100 million years after the Big Bang. The deeper we look into space, the younger the universe appears. This means the night sky is layered with time. Nearby stars represent relatively recent history. Farther stars and galaxies represent ancient eras. Every point of light carries a timestamp. Time in the universe also has a beginning, at least as far as we understand. Current scientific evidence suggests that the universe began approximately 13.8 billion years ago in an event known as the Big Bang. This was not an explosion in space, but an expansion of space itself. Time and space began together in that initial moment. Before the Big Bang, our current theories cannot clearly describe what existed, if anything. Time itself may have begun at that point, meaning there may not have been a before in the conventional sense. The age of the universe, 13.8 billion years, is almost impossible to truly comprehend. To put it in perspective, if the entire history of the universe were compressed into a single year, human civilization would occupy only the final few seconds of December 31st. All of recorded history would fit into a blink. Stars live for millions or billions of years. Galaxies evolve over billions of years. Planets form, cool, and change across immense stretches of time. Compared to these cosmic timescales, a human lifetime is extraordinarily brief. And yet, here we are, aware of time, measuring it, questioning it. Time in the universe also flows forward in a direction known as the arrow of time. This arrow is closely linked to entropy, the tendency of systems to move toward greater disorder. Stars burn their fuel. Heat spreads out. Structures gradually break down. The arrow of time gives the universe its sense of progression from past to future. But on the level of fundamental physics, many equations work equally well forward and backward in time. This suggests that the asymmetry we experience, memory of the past but not the future, may emerge from deeper statistical laws. Time is not only something the universe contains. It is something the universe creates through change. And yet, despite all this complexity, time also gives us perspective. When we realize that the atoms in our bodies were forged billions of years ago in ancient stars, time feels less like a barrier and more like a bridge. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were born in stellar furnaces long before the Earth existed. We are connected to deep time. Looking at the stars, we are not just seeing distant lights. We are witnessing ancient events. We are participating in a grand timeline that stretches across billions of years. Every observation is a dialogue between past and present. Time in the universe humbles us. It reminds us that civilizations rise and fall in cosmic instants. That mountains erode. That stars ignite and fade. that galaxies collide and reshape themselves across eons. But time also elevates us. Because for a brief moment in this vast chronology, the universe has become conscious of itself, through us. We may exist for only a flicker in cosmic history, but within that flicker we ask questions about beginnings, endings, and infinity. Perhaps that is one of the most beautiful truths about time. It gives meaning to our curiosity. The universe is ancient beyond imagination. Yet in this present moment, under a sky filled with ancient light, we stand at the intersection of past and future. And as we gaze upward, we are not merely looking at stars. We are looking back in time, and forward into mystery. For most of human history, the universe was imagined as eternal and unchanging. The stars appeared fixed. The night sky seemed permanent. It was natural to assume that the cosmos had always existed exactly as we see it now. But in the 20th century, astronomy revealed something astonishing. The universe is not static. It is expanding. This discovery began with careful observation. In the 1920s, astronomer Edwin Hubble studied distant galaxies and noticed a consistent pattern. The light coming from most galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. Redshift occurs when an object emitting light is moving away from the observer. The greater the redshift, the faster the object is receding. Hubble found something even more remarkable. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship, now called Hubble's law, revealed a profound truth. Galaxies are not simply drifting randomly through space. Space itself is stretching, carrying galaxies along with it. To picture this, imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. Note it is the center of expansion. The surface itself is expanding. Similarly, in our universe, space between galaxies is growing. From any galaxy's perspective, it appears as though all others are moving away. This expansion implies something extraordinary. If we trace the motion of galaxies backward in time, they must once have been much closer together. Follow this backward far enough, and we arrive at a moment when the entire observable universe was compressed into an extremely hot, dense state. This event is known as the Big Bang. The Big Bang was not an explosion in empty space. It was the rapid expansion of space itself. There was no center into which it expanded and no outer edge. Space and time began in that early, intense state about 13.8 billion years ago. In its first fractions of a second, the universe expanded and cooled with incredible speed. Within minutes, the first atomic nuclei formed. Hundreds of thousands of years later, atoms could finally exist as electrons settled into stable orbits around nuclei. Light, which had previously been trapped in the hot plasma, was then free to travel. That ancient light still exists today. It fills the universe as faint microwave radiation known as the cosmic microwave background. Discovered in 1965. This radiation is one of the strongest pieces of evidence for the Big Bang. It is the afterglow of the early universe, a quiet whisper from a time when everything was unimaginably hot and bright. As the universe continued to expand and cool, gravity began shaping matter into structures. Small density variations grew into stars and galaxies. Over billions of years, galaxies clustered into vast cosmic webs, separated by enormous voids. Yet the story does not end there. In the late 1990s, astronomers studying distant supernovae made another surprising discovery. Not only is the universe expanding, the expansion is accelerating. This was unexpected. Gravity, which pulls matter together, should have been slowing the expansion over time. Instead, galaxies are receding from one another faster and faster. To explain this acceleration, scientists proposed the existence of dark energy. Dark energy is a mysterious form of energy that permeates space itself. It does not clump like matter. It does not emit light. But it appears to exert a repulsive effect on cosmic scales, pushing space to expand more rapidly over time. Today, dark energy is estimated to make up about 68% of the total energy content of the universe. Dark matter, another invisible component that exerts gravitational pull, makes up about 27%. Ordinary matter, the atoms that form stars, planets, and people, accounts for only about 5%. In other words, most of the universe is made of things we cannot directly see. The expansion of the universe shapes its possible future. Scientists have proposed several scenarios, depending on how dark energy behaves over time. One possibility is the heat death or big freeze. If expansion continues indefinitely, galaxies will drift farther apart. Stars will burn out. Over trillions of years, the universe will grow colder and darker. Eventually, only faint remnants, white dwarfs, neutron stars, black holes, will remain in an increasingly empty cosmos. Another scenario, though less favored by current evidence, is the Big Crunch. If gravity were strong enough to overcome expansion, the universe could eventually reverse its growth and collapse back into a dense state. However, current measurements suggest this is unlikely. There is also the speculative Big Rip, in which dark energy grows stronger over time. In this scenario, expansion accelerates so dramatically that galaxies, stars, planets, and eventually even atoms are torn apart. This remains hypothetical, but it illustrates how deeply the nature of dark energy influences cosmic destiny. Despite these dramatic possibilities, the expansion of the universe unfolds on timescales so vast that it does not affect our daily lives. The Earth remains bound to the Sun. The Sun remains bound within the Milky Way. Gravity holds galaxies together against expansion on local scales. The stretching of space becomes noticeable only across immense distances between galaxy clusters. There is something quietly profound about this expansion. It means the universe is dynamic. It is evolving. The night sky we see today will not look the same billions of years from now. In the distant future, galaxies beyond our local group may drift so far away that their light will no longer reach us. Future civilizations, if they exist, might see a darker sky and have no evidence of a broader expanding cosmos. We are living at a time when we can observe and measure the universe's grand structure. The expansion also reminds us that change is fundamental to reality. The cosmos is not fixed or static. It is unfolding, stretching, transforming across unimaginable spans of time. And yet, within this expanding universe, structure and beauty arise. Galaxies spiral gracefully. Stars ignite. Planets form. Life emerges. Conscious beings look up and wonder. The Big Bang was not merely a beginning of matter. It was the beginning of possibility. From a dense, nearly uniform state, the universe evolved into complexity, into stars and oceans, into mountains and mines. Expansion did not prevent structure. It allowed it. The cooling of space enabled atoms to form, chemistry to develop, and eventually biology to flourish. We are products of cosmic expansion. The atoms in our bodies were once compressed in that early universe. The space between galaxies continues to stretch, yet here on Earth, gravity gathers matter into living forms capable of reflection. When we look at distant galaxies racing away from us, we are witnessing the ongoing story of a universe still in motion. The expansion of the universe tells us that everything is part of a larger unfolding narrative, one that began in brilliance and continues in quiet acceleration. It reminds us that the cosmos is not just vast in space, but in time and transformation. And perhaps there is something comforting in that. The universe is not frozen in perfection. It is growing, changing, and evolving, much like we are. In the endless stretching of space, we find not emptiness, but motion. Not silence, but history in progress. The universe began in fire and continues in expansion, and within its widening horizons, we find ourselves, small yet aware, carried gently forward on the tide of cosmic time. When we look up at the night sky, scattered with countless stars, a quiet question often arises: are we alone? For most of human history, Earth was thought to be the center of everything, the only world, the only cradle of life. But as our understanding of the universe expanded, so did our sense of possibility. Today, we know that our Sun is just one of hundreds of billions of stars in the Milky Way. and our galaxy is only one among hundreds of billions of galaxies. In such vastness, it feels natural to wonder whether life exists elsewhere. To explore this question, we must first understand what life requires, at least as far as we know it. On Earth, life depends on a few key conditions. Liquid water is essential. It allows complex chemistry to occur and supports biological processes. Life also requires a source of energy, such as sunlight or chemical reactions, and a stable environment where complex molecules can form and persist. Elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are fundamental building blocks of living organisms. Astronomers use these criteria to define what is known as the habitable zone around a star, sometimes called the Goldilocks zone. This is the region where temperatures are not too hot and not too cold, allowing liquid water to exist on a planet's surface. If a planet orbits too close to its star, water may evaporate. Too far away, and water may freeze. Earth happens to lie in this delicate balance. For a long time, we did not know whether planets were common around other stars. That changed in the 1990s with the discovery of the first confirmed exoplanets, planets orbiting stars beyond our Sun. Since then, thousands of exoplanets have been detected. Some are massive gas giants larger than Jupiter. Others are rocky worlds similar in size to Earth. Some orbit red dwarf stars. Others circle stars much like our own. Statistically, it now appears that most stars in the galaxy host planets. This alone transforms the question of life. If planets are common, and many reside within habitable zones, then the conditions for life may not be rare. Some of the most intriguing discoveries include Earth-sized planets located within their stars' habitable zones. While we cannot yet directly see oceans or continents on these distant worlds, we can analyze their atmospheres by studying how starlight passes through them. Scientists search for chemical signatures, such as oxygen or methane, that might suggest biological processes. So far, no confirmed evidence of extraterrestrial life has been found, but the search continues. Our own solar system also holds possibilities. Mars, once warmer and wetter, shows evidence of ancient rivers and lakes. Robotic missions continue to search for signs of past microbial life beneath its surface. Beyond Mars, icy moons such as Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, hide vast subsurface oceans beneath thick ice shells. These oceans are kept liquid by tidal heating, internal warmth generated by gravitational interactions. On Earth, life thrives around deep-sea hydrothermal vents without sunlight. It is possible that similar environments exist on these distant moons. Life, as we have learned, can be remarkably resilient. On Earth, organisms survive in extreme conditions, in boiling hot springs, acidic lakes, deep underground rocks, and even frozen Antarctic ice. These extremophiles expand our understanding of where life might exist. The search for life beyond Earth also includes the search for intelligent civilizations. Projects like SETI, Search for Extraterrestrial Intelligence, listen for unusual radio signals from space, signals that might indicate technological activity. Given the enormous number of stars and planets, some scientists use the Drake equation to estimate the number of potential communicative civilizations in our galaxy. The equation considers factors such as star formation rates, the fraction of stars with planets, the likelihood of life emerging, and the lifespan of technological civilizations. Yet many of these variables remain uncertain. This leads to what is known as the Fermi paradox. If intelligent life is common in the universe, why haven't we detected clear evidence of it? There are many possible explanations. Intelligent life may be rare. Civilizations may exist but be too far apart for communication. They may use technologies we do not recognize. Or perhaps advanced civilizations tend to self-destruct before spreading far into space. Or perhaps we are simply early, among the first. It is also possible that life exists in forms very different from what we imagine. Our definition of life is based on Earth's biology, but the universe is vast and varied. Could there be life based on different chemistries? Could consciousness arise in unexpected ways? These questions remain open. Beyond science, the possibility of life elsewhere carries deep emotional weight. If we discover even simple microbial life beyond Earth, it would mean that biology is not unique to our planet. Life would be a cosmic phenomenon, not a singular accident. If intelligent life exists elsewhere, it would transform our understanding of ourselves. We would no longer be the only minds contemplating the stars. Yet there is also something profound in the possibility that we might be alone, or at least rare. If Earth is one of the few places where life has blossomed into awareness, then our responsibility becomes immense. Consciousness, culture, art, and curiosity would be precious expressions of the universe, fragile and extraordinary. Whether life is common or rare, the fact that we can ask the question is remarkable. We are made of stardust, standing on a small rocky world, orbiting an ordinary star in a spiral galaxy, and we are searching the cosmos for company. The search itself is an expression of hope. Every time a new exoplanet is discovered, every time a telescope scans a distant atmosphere, every time a radio antenna listens to the quiet sky, humanity extends its senses outward. And even if we never find another living world, the quest changes us. It reminds us that Earth is not isolated in darkness, but part of a grand cosmic setting. Perhaps one day we will detect a faint signal, a pattern that cannot be explained by natural processes. Or perhaps a robotic probe will uncover microbial fossils beneath Martian soil. Or perhaps future generations will develop technologies beyond our imagination and glimpse life on distant shores. For now, the universe remains silent. But silence does not mean emptiness. It means the story is still unfolding. As we gaze at the stars and ask, are we alone? We are expressing something deeply human, a desire to connect, to understand, to belong within the vastness. And whether or not other beings share this cosmic stage, we know one thing with certainty: life exists here, on this small blue planet, in a quiet corner of the Milky Way. The universe has grown eyes to see itself and a mind to wonder. That alone is extraordinary. After traveling through vast distances, ancient light, exploding stars, black holes, and expanding space, we return to a simple and deeply human place, ourselves. What does it mean to know that we live in a universe 13.8 billion years old? What does it mean to realize that Earth is a small planet orbiting an ordinary star in the outer arm of a spiral galaxy among billions? At first, this knowledge can feel overwhelming. It can make us feel small, almost invisible, in the cosmic scale. And yet, there is another way to see it. Yes, we are small in size. Yes, our lives are brief compared to stars. Civilizations flicker in time like sparks. Mountains erode. Oceans shift. Even galaxies collide and reshape themselves over billions of years. But small does not mean insignificant. A single neuron in the brain is tiny, yet without it, thought cannot exist. A single musical note is brief, yet without it, a symphony would be incomplete. In the same way, our smallness does not diminish our meaning. In fact, the universe becomes meaningful to us precisely because we can perceive it. Among the countless stars and planets, as far as we currently know, there are very few places, perhaps only one, where matter has arranged itself into beings capable of awareness. At least here, on Earth. The atoms forged in ancient stars have become conscious. They ask questions. They feel wonder. They create art and science. They love. There is something quietly astonishing about that. The iron in your blood was formed in a supernova billions of years ago. The oxygen you breathe was created in the heart of a star. The carbon in your cells once drifted through interstellar clouds, over immense stretches of time. Gravity gathered these elements into new stars, into planets, into oceans, and eventually into you. You are not separate from the universe. You are an expression of it. When we look at the night sky, it can feel as though we are observers standing apart from something distant. But in truth, we are participants in the same cosmic story. The universe is not just out there. It is within us, in our bodies, in our breath, in our thoughts. This realization often brings a sense of humility. We are not the center of the cosmos. The universe does not revolve around human concerns. Stars are born and die without regard for our existence. Galaxies collide on timescales far beyond our lifetimes. This can feel unsettling, but humility can also be liberating. When we accept that we are part of something vast, we release the illusion that everything depends solely on us. We are threads in a tapestry far larger than we can fully comprehend. The pressure to be central fades. In its place comes a sense of belonging. The universe does not exist for us, but we exist within it. There is also a quiet peace in contemplating cosmic time. Many of our daily worries, deadlines, arguments, temporary failures, shrink when viewed against billions of years. This does not mean they are unimportant. It simply means they are not everything. Under a sky filled with ancient stars, perspective expands. Science, often perceived as cold or purely analytical, reveals deep beauty. Equations describe the bending of space-time. Telescopes capture faint light from galaxies billions of light-years away. Data points map the expansion of the cosmos. But behind these measurements lies something profoundly poetic, the desire to understand. Science is not just a collection of facts. It is a human expression of curiosity. It is the act of reaching beyond immediate experience and asking, why? And how? When astronomers measure the cosmic microwave background, they are listening to the echo of the early universe. When physicists study black holes, they are exploring the limits of reality. When biologists search for life beyond Earth, they are extending the question of existence itself. There is wonder in that pursuit. And there is beauty in the idea that a species on a small planet can decipher the age of the universe, measure the speed of light, and detect planets orbiting distant stars. The universe may be vast and indifferent, but it is not meaningless. Meaning arises wherever awareness arises. Some people find comfort in the idea that humanity is unique and central. Others find comfort in the idea that we are one part of an immense cosmic family. Both perspectives attempt to reconcile scale with significance. Perhaps the truth lies not in size, but in connection. We are connected to the stars through physics, connected to the Earth through biology, connected to one another through shared experience. When we stand beneath a dark sky and look upward, we participate in a tradition older than recorded history. Our ancestors looked at the same stars, though not in exactly the same arrangement. They created myths, calendars, and stories to make sense of the lights above. Today, we have telescopes and equations, yet the feeling is similar. A mixture of awe, curiosity, a quiet sense of mystery. The more we learn, the more we realize how much remains unknown. Dark energy, the true nature of black holes, the origin of consciousness, the possibility of other universes. Knowledge expands, but mystery does not disappear. It deepens. And perhaps that is the most beautiful balance, understanding and wonder existing side by side. We may never fully comprehend the totality of the cosmos. The universe may be too vast, too complex, too ancient for any single mind, or even any civilization, to grasp entirely. But we do not need to understand everything to appreciate something. A single clear night. A glimpse of the Milky Way stretching across the sky. The awareness that the light reaching your eyes began its journey long before you were born. In those moments, the universe feels both immense and intimate. We are small, yes, but we are not separate. We are a brief, luminous chapter in a 13.8 billion year story still unfolding. And perhaps the greatest wonder is not that the universe is vast. It is that within that vastness, something has emerged that can feel or ask questions, and quietly whisper, I am here. We began with a simple question. Have you ever looked up at the night sky and wondered where we are in this vast universe? Now, after traveling through galaxies, stars, black holes, cosmic time, and the possibility of life beyond Earth, we return to that same sky, but perhaps we see it differently. The universe is vast beyond easy comprehension. The observable cosmos stretches for about 93 billion light-years in diameter. It contains hundreds of billions of galaxies, each with hundreds of billions of stars. It has existed for 13.8 billion years, expanding, cooling, evolving. It is ancient. It is immense. It is still full of mysteries. We have learned that Earth is not the center of everything. It is a small rocky planet orbiting a medium-sized star in the outer region of the Milky Way. Our Sun is one among countless others. Our galaxy is one among billions. And yet, this knowledge does not reduce us. It refines us. The Milky Way, our cosmic home, spins slowly across hundreds of thousands of light-years. Stars are born in glowing nebulae and die in brilliant explosions. Black holes anchor galaxies. Space itself stretches, carrying galaxies farther apart. Time bends. Light travels across billions of years. When we look into the distance, we are looking into the past. And in all of this, in the quiet drift of galaxies and the fiery birth of stars, matter has organized itself into something extraordinary: awareness. We are part of the universe becoming conscious of itself. The atoms in our bodies were forged in stellar furnaces. The elements of life were scattered across space by supernovae. Gravity gathered them into new stars, new planets, and eventually into oceans and cells. Over billions of years, chemistry became biology. Biology became perception. Perception became thought. And now, here we are, asking questions about the very process that made us possible. There is something deeply humbling about that. We are small in size, brief in duration, and limited in perspective. Our lives unfold in decades, while stars burn for billions of years. Civilizations rise and fall in cosmic instants. Compared to the age of the universe, all of human history is a fleeting moment. Yet within that fleeting moment, we have measured the speed of light. We have mapped distant galaxies. We have detected planets orbiting stars hundreds of light-years away. We have listened for faint whispers from the early universe. We may not understand everything, but we understand enough to know that the universe is larger and older than we once imagined. And perhaps that is enough. The universe does not promise certainty. It offers mystery. Dark matter and dark energy still puzzle us. The true nature of black holes remains partly hidden. The origin of the Big Bang raises questions beyond our current theories. The possibility of life beyond Earth remains open. Mystery is not a weakness of science. It is its horizon. Each discovery expands the edge of what we know. And beyond that edge lies more to explore. When we reflect on the cosmos, we may feel two emotions at once: smallness and belonging. Smallness, because we are not central or dominant in the grand scale of existence. Belonging, because we are made of the same substance as the stars. We are not visitors in this universe. We are participants. The night sky, once thought to be distant and unreachable, is in fact our extended family. Every photon of starlight that reaches your eyes connects you to an ancient source. Every breath you take contains atoms that once drifted through interstellar clouds. In this sense, the boundary between us and the universe becomes softer. Science teaches us structure and scale. It gives us numbers, measurements, and models. But beyond the data lies something more subtle, a quiet sense of wonder. The beauty of the universe is not only in its size or complexity. It is in the way it invites reflection. It invites us to pause, to look up, to think beyond immediate concerns. Under a sky filled with stars, daily anxieties grow quieter. Perspective widens. We realize that we are part of a story much larger than our individual lives. This does not make our lives meaningless. On the contrary, it makes them precious. Because in a universe so vast and ancient, conscious moments are rare and fragile. The ability to feel or to ask questions, to love, to imagine, these are not small things. They are extraordinary. Perhaps the greatest gift of studying the universe is not knowledge alone, but humility. The understanding that we do not stand above nature, but within it. That we are woven into the same cosmic fabric as galaxies and nebulae. And perhaps there is peace in that realization. We do not need to conquer the universe to find meaning. We do not need to solve every mystery to appreciate its beauty. It is enough to look up and know that we are part of something vast and unfolding. The universe will continue to expand. Stars will continue to form and fade. Galaxies will drift across unimaginable distances. And for a brief moment, here and now, we are here. Aware, curious, alive. Maybe the most beautiful truth is not that we fully understand the universe. Maybe it is that we can stand beneath it, lift our eyes to the night sky, and feel its immensity. To know that we are small, yet connected. Brief, yet meaningful. One tiny chapter in an ancient and ongoing cosmic story. And perhaps the most beautiful thing of all is this. We may never understand the universe completely, but we can always look up and quietly feel its vastness.